Okay, so we'll actually get started. I guess some time. So the midterm is done. I got the sheets, and I have to look at them at some point of time. And then Karthik said he's been sending you guys emails on the review part, the paper reviewing thing, and that is going to be, I mean, that's for credit. I mean, so you have to do that as part of, the related work for this class. However, it's just asynchronous. That means it starts and it goes on in the background, and he will be telling you what the deadlines are for those. It's like basically two things that you're supposed to get out of it. One is, of course, if you haven't already, one is that you want to just read papers that are at the current state of the art, connected to presumably MDPs and reinforcement learning, because that's what I assume most of you selected. I don't quite remember what you selected. And then understand them. So that's one thing. The other question, of course, is also to get a feel for what it is like to actually defend your reviews, when you actually do conference reviewing, although you will be mostly defending among yourselves, because I think the way it's going to work is apparently for each, I think tomorrow is the deadline for you to bid, right? And then he will give each of you two papers to review. One would be the paper that you have chosen, so you will get to review that, and one would be another paper. Okay, and so everybody gets to review the paper they chose, as well as one more paper on which they bid, hopefully. And then this is normally the way conferences work anyway. Of course, however, there's always this usual thing that the popular papers get lots of bids, the unpopular papers get very few bids. As to popular versus unpopular is decided by the number of bids, essentially. So I think NIPS this year had statistics. If I get it, I'll send you. I think the most popular paper in NIPS this year had 74 bids, and they only need 3 reviewers. So 74 people were dying to read this. Okay, and then the least popular one apparently for them had maybe like 4 bids or something. It's not too small actually, surprisingly enough. And not surprisingly, I don't know, maybe or maybe not, it's not surprising. So the least popular paper did get accepted, and the most popular paper did not get accepted. Okay, if people are dying to read your paper, it's most likely that they're also going to kill it, right? because they've been trying to do this problem, and then suddenly your heading says you have solved it, and they are going to look at it. So careful what you wish for. You want to be popular after publication, not before, because if you become popular before, then you won't get published. But anyway, I don't know exactly how it's going to happen for these particular papers here, but there would be some, unevenness. But each of you will get 2 papers to review, and you will, in the first phase, you will be just entering your own review, and in the second phase, you would be, once you enter your review, you will then see the other person's review. For each paper, there are 2 people, 2 of you here, okay? And then you will look at each other's reviews and you discuss. That's what happens in the normal conferences. And it's this discussion phase, since we are also converting this into sort of a graded homework, okay? So we will have, in normal conferences, essentially, they will have a senior program committee member who would ensure that the reviewers actually discuss, okay? So we will play the role of senior program committee member. So each one of the papers will have either me or Karthik or Tuan or Sushavan or Yuheng or one of these more senior people be involved, okay? And there's no right or wrong. I mean, you can very well have a differing opinion about a paper. It's a question of how do you defend it, okay? That's kind of what we'll hopefully try to learn. And again, this is, to some extent, this is a completion credit kind of an assignment. We are not going to be able to differentiate 97 points worth of work versus 93 points worth of work versus 67 points worth of work. But at the same time, I think it's, rather than, I used to have people just read papers and type the discussions onto the blog, but nobody reads them. And even I would have a hard time after the first paper. And so this way, at least somebody else, is reading, and you're trying to also defend it, in front of an SPC number. So that's what that particular assignment is, and that is asynchronous, and it will have its own deadlines that Karthik will be telling you about, and you need to deal with them. We will have most likely a homework on PalmDPs that will be coming up. As I said, you will have one on that, and then there's going to be a project on LDA, latent directional allocation. It's sort of a, mostly using an existing code base to, apply LDA to something. And then you might have also a homework on the graphical models, which is basically the next big topic. Okay, so that's where we are going with the semester. Any questions? Okay, so before I go off to the graphical models, by the way, for the graphical models, it turns out that although you are supposed to know Bayes networks, I'm going to go over them very quickly in the class, and then I might make it like partly you watch the videos and then we discuss sort of thing, so that I can get that part done, the stuff that gets done normally in 471, done quickly, so that we can focus on other interesting things such as learning and also templated Bayes networks, which is basically what LDAs, latent digital allocation is. Okay, so that's what we'll be doing on that. And then one other logistical issue is next Wednesday, if you actually looked at the list of the lectures, I think I said Rao would be on travel, but it turns out that my flight is only at 5:30, and I just became the silver preferred member for US Airways, which means that apparently I can just walk over people's heads and walk to my gate. So what I'm going to do is actually I'll teach until 4 o'clock. And then so it'll be a slightly shortened class. Maybe I'll start on dot, and then we'll go up to 4. And so I'll leave you 15 minutes ahead, and then I'll drive to the airport. Okay, so that's what we're going to do. Okay, so that's the scenario. Any questions? Anything else? You had a question? No. Okay. Okay. So one thing that I sort of felt I should do before we go off to these graphical models is, so the graphical models are going to be propositional representations of probability distributions. Okay. We have been looking mostly at atomic representations of MDPs, PalmDPs. Okay. In between, we it wasn't that you never heard of factored approaches. So for example, those of you who have done 471 before know strips action representations. Those are obviously factored representations. Also, when you read, for example, FF hop, that was using factored representation. And in fact, the question that I had about numbers sort of starts with, the n Boolean variables, and then of course if you have n Boolean variables, that is a factored representation. Okay. However, we mostly understood how to do optimal policies for MDPs and PalmDPs in the atomic space, and I've been sort of telling you that we will get to the propositional or the factored one. And the tricky part about doing that is while where am I right now? Okay, so while the MDP, PalmDP classical methods sort of are nice, a coherent small piece where I can pick an algorithm and analyze it, etc. There's a whole lot that's been going on. It's all over the place in terms of various ways of factorizing these MDP methods. Okay, so there are basically, depending on the representation you use for representing your actions, representing your value functions, representing your reward functions, you can get very different types of algorithms for doing inference and learning. Okay, so what I would be doing today is at least to give you an idea of what are the advantages for using these factored methods and what are some of the representations that people use currently. But there's just so many different papers on them, one paper each on one type of representation. And so there is no, it's not going to, it's more of a, this lecture is going to be more of a overview lecture of, what kinds of techniques are available out there, okay. Anyway, so if you remember, I guess factor representations, this is sort of the overview. If you get this at the end of this lecture, then you got, the basic point of what I'm trying to teach. So we basically, of course, had POMDPs and MDPs, and both of them were using atomic representations. Atomic representations for what? States, actions, reward functions, value functions, and policies, right? Okay, they were all represented atomically, and of course, everything flows from the state representation. The moment states are atomic, then everything else becomes atomic. Okay, and so what we would like to start with is, in a factored representation, in a propositional representation, states obviously are going to be, having structure, so state variables. Okay. Again, by the way, it turns out I'm just mostly focusing on propositional or factored, propositional or attribute representations here. In fact, there is some more work which focuses on first order representations for MDPs and POMDPs. Okay. But it becomes more and more esoteric. There may be a few papers, and there's interesting research topics, but it's still not clear that I could teach you a coherent lecture. Okay. So even though so we talked about state and atomic, and we are mostly looking here at propositional, and then there are also first order representations for these things. Okay. So when you're looking at states with structure, normally you think of them as states made up of state variables. Okay, there are some people who think of them as state variables, some of them think of them as features, some of them think of them as attributes. They're all equivalent. Okay, states have properties. Okay, and then the assumption is if you give all the properties of the state, then you have defined the state. Okay, the simplest kind of properties are, it has a bunch of Boolean properties which can be true or false. And if there are n such Boolean properties, then obviously you get to distinguish between 2 power n states. That's what we've been, talking a lot about. You could also have, n, devalued variables. That means multi-valued state variables, d not being 2, it can be 3, 4, etc. In which case, instead of being 2 power n, it will be d power n. Okay, that's possible too. Okay, multi-valued representations. You can also have, of course, continuous features. You can have, not Boolean but continuous features. Okay, and we don't talk too much about continuous features here, but those are, of course, possible. Okay. So now the moment states become part of, defined in terms of these features, we have talked about this before. The thing that changes because of that is now actions can use the structure of the states. One thing that you want to keep in mind is, starting from here, every place you get to decide whether to use the structure or not. Okay, so for example, I might have given you states with structure. You might decide, I really don't want to look at the structure, so I'll right away compile it into 2 power n Boolean and atomic states and go back to my happy life, wherein I get to talk about actions directly in terms of the states. Okay, but the point, of course, is if you do actually have structure for the states, it turns out you can provide more compact representations for actions. And in fact, I mentioned this in the very beginning of the course. If you have atomic representation, each action is essentially an S by S matrix. Okay, no bigger, no smaller. If S is a huge number, each action requires a large space to define. Okay, typically we are able to live in the worlds we are able to live in, even though our worlds have a huge number of states, because each action tends to change just a few of the properties of the state. You see what I'm saying? So even though ultimately the actions can be seen as these huge matrices, they are highly sparse matrices. Okay, and they become sparse because essentially actions have locality. They tend to change only a few state variables. Now, there is no God-given rule about this. It's just that if every action changes every state variable in the world, then we needed a much bigger brain or we won't be here. Do you understand what I'm saying? Okay, so the world we live in is either by design or by luck is reasonably factored, and the actions are localized. That's why we are still around. Okay, so we want our robots also to be, our agents also to be able to exploit that locality. Okay, and in an atomic representation, there is no way of exploiting that locality because all actions would be of S by S size. Whereas in a propositional representation, we'll see that actions only talk in terms of the variables that they change. You see what I'm saying? So they can have much more compact representations. And those of you who remember strips actions, obviously strips is an example of these kinds of actions. Okay, strips actions will essentially, an action says it requires some preconditions which says variable v1 must be true, variable v2 must be false before this action can be done, and after the action is done, v5 would be forced to true and v7 would be forced to false. And then it doesn't say anything about any of the other variables, for example. What happens? Those variables just stay what they were before. So that's the big deal about strip action representations. Okay, so we'll see that actually there are obvious alternatives for action representations. Strips is just one, and then we'll at least see this idea called 2 time slice dynamic Bayes nets. They're just two different action representations. There are many different action representations that you can potentially think of. Okay, either of these will be able to use the structure available in the states. Okay, now having done that, the next question is how do you represent the reward and the value functions and the policies too? Okay, value functions and also policies actually. Now, all of these two, again, you get to say, I'll just talk directly in terms of extensional tables of state to the reward, or you could say they are some arbitrary functions over these state variables. Right? Okay. So, for example, I could say the reward of a state is, 2 times variable 1 plus 3 times variable 2, assuming these are, let's say, discrete valued variables. That's the reward. I can make that. Okay. So that would be sort of a linear, feature-based representation of the reward function. Okay, another idea would be to start and write a decision tree kind of a representation for the reward. You can say, well, to figure out what is the reward of a state, I have a decision tree sitting there. Okay, the decision tree says, is the variable v1 true or false? If it is true, then you get 0.5 reward. If it is false, then I want to know, is v2 true or false? If it is true, you then get 0.3 reward. If it is false, then I might ask some more questions. You see what I'm saying? This structure looks like a decision tree. Okay, and these are called ADDs, arithmetic decision diagrams. Okay, and they are generalizations of another representation called BDDs, which are binary decision diagrams, where the leaf nodes in ADDs are numbers, real valued numbers. The leaf nodes in BDDs are true false values. Now, the interesting thing, of course, is anytime I mention a representation, I could actually spend classes talking about expressiveness of that particular class of representations. And there are huge books written on it. So, for example, BDDs. How many of you, or any of you heard of BDDs in the class? You did. So, what's BDD? Where are they used? No, so where are BDDs used typically? So tell me one big company which depends on BDDs. Intel. Okay, circuit verification is pretty much depends on, circuit verification requires essentially whether certain logical formulas will hold invariant over the circuit. Okay, this requires essentially reasoning with arbitrary logical formulas. Okay, now even in propositional logic, you can have, I can give you two logical formulas and they are equivalent, but they look completely different from each other. Do you understand what I'm saying? So the simplest one that you know is here, I can give you this and this. These are completely different looking formulas, but you know they are equivalent, right? Okay, but this is the easy one. This one you know in textbook. But I can give you a formula which is made up of 1800 propositions. Okay, and another formula which is also made of 1800 propositions. And I ask you, are they same? It turns out it's a very hard problem. It's essentially an NP-hard problem to check whether two formulas are equivalent. Okay, and this check is needed a lot in circuit verification. And so one question, of course, is look for canonical representations for Boolean formulas. Okay, any of you know Boolean formula canonical representations? Like the DNF and CNF. Okay, DNF and CNF are canonical, but they are not unique. Okay, that means I can take any arbitrary logical formula with all sorts of connectives and write it as a set of DNF clauses or a set of CNF clauses. However, I can give you two sets of CNF clauses and they're equivalent, but you can't tell that just by looking at the clauses. By the way, as I'm saying this, has anybody cared about what do I mean by equivalent? Why are these two equivalent? The truth tables are the same, or the models, the set of models are exactly the same. A model, an interpretation is a truth falsity value over, this is stuff that we do in 471 or any logic course you may have done. Okay, an interpretation is a truth falsity assignment over these variables. Okay, if under an given an interpretation, you can check whether or not the formula evaluates to true. If a formula evaluates to true under an interpretation, that interpretation is called a model. Two formulas are considered equivalent if the sets of models for both of them are exactly the same. The sets are equivalent. That's what we mean by equivalence. Now it turns out that BDDs are a representation, especially what's called ordered binary decision diagrams, OBDDs, or even reduced ordered binary decision diagrams, ROBDDs, basically have this property that if you take any arbitrary Boolean formula and give it to an ROBDD compiler, it'll spit out a nice BDD which looks like this. Okay, and if we give another equivalent formula, it'll spit out the exact same BDD. Okay, and furthermore, a lot of operations, the logical operations can be done very efficiently on BDDs. And they're so big that the guy who actually did a lot of work on this is right now the dean of Carnegie Computer Science Department, School of Computer Science, Randy Bryant. And didn't he get a Turing Award? He got one. Okay, so just for doing this, basically developing techniques for reasoning about BDDs. So I could just say BDD here and say ADDs are nothing but generalization of BDDs and we just use it, right? But if you really want to understand that representation, then I have to make a big digression and talk about BDDs. And there are actually books written on BDDs and how to manipulate those representations. Okay, so that's one of the unsatisfactory things about teaching about factored approaches, because you get to decide which representation you use, and based on that representation, first you need to understand that representation, the expressiveness of it, and then you need to kind of write your algorithms in that representation. Okay, yes?
Isn't the state equivalence or the sex equivalence different from the definition of truth table equivalence?
What?
You said the PNQ would be equivalent when their states are equivalent.
No, their models are equivalent. The models means essentially the models are the rows in the truth table for which the function evaluates to true. Two formulas are considered equivalent if the rows in which they evaluate to true are exactly the same. Okay. Anyway, so you can represent reward and value functions as BDDs. You can also represent them, as I said, as these linear functionals. Which one is better? I don't really have any obvious stake in this. In fact, many people who do exact inference on MDPs tend to use the ADDs, arithmetic decision diagrams. Okay, many people who use the representations of value and reward functions as part of reinforcement learning tend to use these representations. In fact, we'll see that. Okay, one of the neat things, as we'll talk about in the next column, once you get these representations, the question is, what are the advantages? Who are we trying to impress by going factored? Okay, and it turns out, they have bunches of advantages, and one advantage comes in learning, and the learning is again connected to representations. Learnability depends very much on what's the representation of the hypothesis you're trying to use. You see what I'm saying? And lots of people know how to learn the coefficients for linear expressions by using gradient descent methods. And if you haven't heard it, I'll say a little about it. And then by the end of next several classes, you would know enough about gradient descent as a way of learning. Okay, but there are fewer learning approaches, for example, for ADDs. Although decision diagrams, decision trees are, a kind of a learning approach. Okay, so I hope I'm trying to get to you is that although upfront when I'm talking about how do I capture the structure, I should use representation. Looks like any representation is just as good as any other. The moment you take a particular direction, then you need to know about the properties of that representation and the expressiveness of that representation and doing the inference in that representation and doing learning in that representation. Okay, question, yeah.
So I noticed in the schedule for next semester there's a class on knowledge representation. Is it going to cover some, is that what this
knowledge representation? Knowledge representation would basically cover logical representations of the world. I mean, it should cover anything, but it depends on who is teaching it. I think it's being taught by Ju-Hyung, right? And Ju-Hyung Lee, and he likes a lot of logical representations. He would not cover probabilistic representations, for example. But, it turns out just logical representations of the world, you require multiple courses to just understand everything about it. Okay, so that's the thing, basically the choice you make here is connected to the expressiveness of those representations. And there was any other question before I move on? Okay, so that's one idea. The other thing, of course, is once we get the representations going, then we get to talk about who are we trying to impress? If we get a representation, factored representation, what's going to happen? Okay, now of course, just as I said, after you decided to have structure for the states, you could have decided not to use it for the actions or the reward functions. Okay, having used it for the actions and reward functions, you can still decide not to use it, for anything, such as specifying the model or inference, doing the value and policy iteration or learning. It's up to you. Okay, it turns out that we will talk about if you do use it, there are some advantages. Actually, learning, you almost have to use it, but specification, essentially, if I'm trying to specify a Markov decision process, for example, it would be much easier for me to talk about states in terms of their properties and actions in terms of what properties they change, and reward functions in terms of any state where this property is greater than 5, you get 2 units of reward. There, I said it. Now, all those states, reward function has been specified by just one single sentence. Do you see what I'm saying? Okay. So specification is very useful. In fact, even when people use atomic representations for the inference, they tend to at least provide the ability to eat the factored representations. So many of the MDP solvers, except for the simple ones that you may have looked at where it's just a grid or something, many MDP solvers provide some reasonable language in which you get to talk about the states and the rewards. And then they may just decide to convert the whole thing into atomic representation and do the dirty work. Do you see what I'm saying? But at least, the interface is at a high level. And this actually happens, if I get there, this actually happens in planning competitions. Probabilistic planning competitions have to provide an MDP. And they provide MDPs in terms of strips actions and state variable, Boolean state variables. But most people in taking part in these competitions, many of them just actually use off-the-shelf state-based, atomic state-based approaches for policy and value iteration. You see what I'm saying? So it's kind of important to understand that just because you chose to write it in higher level doesn't necessarily mean you have to solve it in higher level. You right away compile it and the Intel assembly language does it. Okay. Now, of course, so that specification at least is easier. In fact, this is more or less the way, while you are talking about this, you should be thinking in terms of why aren't we writing programs in assembly language, right? We write programs in higher level language, but our machines work in assembly language. And the idea is specifying the program is easier. Debugging the program by yourself is easier if you write it in higher level language. But then finally, it still gets converted into an assembly language. See what I'm saying? But then, even in programming languages, there are, I think this, the next point is that what if I can actually develop my inference algorithms? For MDP, the main algorithms are what? The value and policy iteration, right? Policy finding. And then for POM-DPs, you also throw in the state estimation. Okay, what if I throw all of those? What if I throw all of those also into, I also change them such that they directly work on the factored representations. They don't first convert them into atomic and then do the work and then reconvert it back. Do you understand what I'm saying? Okay, that is where things get quite hairy. Okay, so there are lots of people who, for example, let's say they'll take an ADD representation and they will provide a way of doing Bellman backup directly in terms of the ADD representation. Now notice that Bellman backup is normally done on value of a single state. Now in a factored representation, you have a huge hairy value ADD. That is for the value function for the entire MDP. And you do one Bellman backup, you get a new value function, which is again ADD. Do you see what I'm saying? So each iteration, you are essentially getting a new ADD. And after a while, you stop. And then whatever ADD you have left, that's the value function. You see what I'm saying? Okay. Now, what you could have done is taken the ADD of the value function, converted it into an extensional representation, done the value iteration, and then get the value function, and then convert it back to ADD. You could do that. Then you are not impressing anybody in terms of efficiency because you did all the work in the lower level. Whereas if you can change the underlying steps of your algorithm to work directly off of these representations, you could do much better efficiency-wise. However, the reason these things haven't taken over yet is because actually writing those algorithms, what looks like a simple 3-line code in like value iteration code would look much hairier, because it's now converting directly. The entire ADD is being converted by actions, all the actions together into an entire new ADD. Okay, let me just quickly go forward and give you a picture so that you will see what I'm trying to say. Okay, so here is a value function v0. And then after step 1, I get this value function. And after step 2, I get this value function. I need to support this. That's what I need to support when I'm directly doing the value iteration in my representation. For inference, it almost looks like an albatross for most people. Okay, why did we get into this? We were happy we understood how state-based value iteration works. Whereas these things are actually, much more painful to understand. Okay, and what is worse is for many benchmarks, it's hard to show that the algorithms that do these are as efficient as the algorithms that work directly off of the atomic state representations. And I don't know, you guys know RISC architectures, right? Now, before you were born or before you started going to grade school, there used to be highly micro-coded machines, which essentially avoided this idea that if you write a higher-level language, the first thing you do the moment the machine is switched on is it converts the higher-level language into assembly language. They tried to provide at least language-specific machine support. Highly micro-coded instructions could be done. Okay, and they finally, and in fact, there used to be this thing called Lisp machines, and everybody was supposed to have one of those. Because these are machines that do Lisp very fast. Okay, and then Sun Microsystems, which already is, all these things are like detritus of, I guess, history. But at one time, Sun Microsystems came along and said, hey, you could do RISC. Just basically, let's do just reduced instruction set. And if you have reduced instruction set, if it's a simple set of instructions, then I can do iteration 1, iteration 2, iteration 3 on the dot every year. A new microprocessor will come out. And the speed of that would be compared to this highly micro-coded thing, which to take from 1 year to the next year without bugs would take forever. So micro-coded machines fell off the wayside, and RISC machines just took over. You see what I'm saying? Okay, now you can argue that if we were smart enough to improve micro-coded machines, they would still be, running the show. But we don't question why we are not smart enough, And similarly, if you could argue that if we can actually provide efficient algorithms for doing direct value iteration on ADD space, they would always do better than state level. The problem is many more people are trying to improve state level approaches, atomic state level approaches to value iteration. And very few people are actually doing it at a factored level. And even in the few of them, some are doing on the ADDs, some are doing on the linear representation, some are doing on some other representation. So there isn't enough, human power directed at improving these algorithms. So that sociology of science plays into it, and then essentially in the inference, it's hard to still use, factored approaches. You should know how they work, but they are, oftentimes somebody, can convert this down to atomic representations and then do some faster approximations there. And keep all this information, by the way, back in your head, because when we talk about Bayes networks starting next week, okay, one of the interesting questions would be Bayes networks start at a higher level. Bayes networks don't exist at atomic level. They only exist at propositional level. But you always want to say, if only I was at a higher level than where I was, right? So Bayes networks, having understood how propositional Bayes networks work, we'll start wondering, why can't we have relational Bayes networks? That's like the biggest thing. If you go to any AI conference now, it's all about relational probabilistic models, PRMs. Okay, and then they also have, and some other people who are even crazier say, why not, what's all these PRMs? We really want first order probabilistic models. Okay, now the interesting thing is, again, when we think of PRMs, it turns out many a time PRMs are great for specification, but most people who use probabilistic relational models directly convert them into atomic models, into propositional models, and use efficient algorithms on the propositional models. The same questions that happened here will come there. You see what I'm saying? But the fact that we can't do it right now doesn't mean it can't be done. It's just a question of research going on. Okay, there is in PRMs, for example, there are lifted methods which directly work in the relational level, and then there are also propositional methods which go down to the propositional level and use off-the-shelf approaches. Similarly, here too, there are methods with lifted methods which directly work on the ADD representations, for example. And there are also methods which will just come down to the state level and go up. Okay, so that is one thing. Now, the couple of things, so that's so in terms of the policy and value iteration, especially the value iteration, Bellman backup, you want to do it directly in terms of the representation you are using. And so, the exact specifics of the algorithm depends on the representation. That is the point I'm trying to make. The other interesting thing actually is that there are certain kinds of approaches. There are certain kinds of approaches which actually will become feasible when you start thinking at this lifted level. One is this idea called the policy gradient approach, where you want to essentially start with a policy and locally optimize it so that it becomes better. Okay, do local search in policy space. Okay, that point is very well connected to this learning too. The question, of course, is nothing stops you from locally optimizing the policy space, even in extensional representation of the policy. An extensional representation of the policy would be an SY, it would be an S-sized matrix, right? Which for each state you say what action you're supposed to do. Changing it means changing like one of the states once, small changes. What if I represented this entire policy in a lifted form? Suppose I said the following thing. Whenever feature 4 is greater than, feature F5 is greater than 20, do going up action. Otherwise, do going down action. That's the policy representation now. So for every state, I just look at that particular feature. Based on its value, I know what action I'm supposed to do. You see what I'm saying? Now, when I'm changing local changes to this policy, essentially that would be like changing the thresholds on the features, for example, or adding more features into the mix. And these would wind up having much more interesting changes. Each local step is going to change the policy a lot more. Okay, and so in fact, there are approaches which basically do what's this policy gradient approaches, which directly move in the space of policies, in the space of lifted policies. And those can actually be quite effective. And those of you, did I mention the inverted helicopter here? Did I make you? So inverted helicopter does policy gradient approach. There you go. Okay. So now the interesting question, of course, is they had a simple way of representing the entire policy in terms of this lifted approach, in some lifted representation. And they were able to then support local changes to that policy and do local gradient descent. Okay, that's an advantage that you get because you have lifted representation. And then finally, the biggest advantage you will get if you have lifted representations, and you will not get if you don't have lifted representations, is learning. Remember, I spent so much time when you didn't hear one bit about it, trying to tell you that, can you think of a learning algorithm that works at atomic level? At the beginning of the semester, you didn't know one. But now you know, reinforcement learning is one. Every other learning algorithm you learned ever about are propositional or higher up. Because otherwise, how can you generalize a state-based, if all I tell you is this social security number gets a passing grade, this social security number gets a failing grade, and I give you a whole bunch of students' social security numbers and their grades, what can you learn? Nothing. Unless you are into numerology and add up all the digits in the social security number and try to look for patterns there. If on the other hand, I made up features and said, all the students who got greater than 50, I gave the, the values of their, how they did in different assignments. Okay, so the student is represented by this column of, their grades in the various assignments. And then there is a final grade. Then I can learn. I can learn a generalization. You see what I'm saying? So it turns out that generalization is something that just comes front and center if you use lifted representations. Okay, and so in fact, reinforcement learning people use it pretty much all the time. And that's why in the chapter 17, which talked about MDPs, you did not hear much about the representations for policy and value using ADDs. But in the chapter, I believe 20, the reinforcement learning chapter, Stuart Russell writes about how Q-learning can be directly implemented when the Q value is represented as some sort of a linear combination of features. And the Q-learning updates would then be changing the coefficients of this Q value representation. Do you see what I'm saying? Okay, so you wind up getting, you basically try to learn a single, once you get to this lifted representation, you're trying to, rather than say for state S59, the Q value is this, for state S75, the Q value is this. Instead, what you're trying to do is you're trying to learn, especially if you're using some kind of a linear feature approximation, you're trying to learn WIFI sigma. So given any state, let's say, any state action combination, in fact, let's look at just the value first. Any state, the value of that state is basically representable in terms of WIFI, where FI are known features of the state, for which the moment you see the state, you know what the values of the features are. WI are some things that you learn. Okay, and when you are changing that, the Q learning updates or the TD learning updates, previously, anytime you updated, you just learned the new value of one guy. Now, in trying to set the new value of one guy to be close to its predicted value, you wind up changing these WIs. Your interest is just to make sure that this state 55 agrees better with its neighbor. But the only way you could do it is to change this formula. The moment you do that, you wound up changing the WI, so you change the values across the board. You can say that is a bug or a feature. You can say that's a bug if you think every state is completely different from every state, and when I'm trying to learn the value of this state, why should I even be touching anybody else? In which case, you should just be doing atomic reinforcement learning. You can see this as a huge feature if you realize that really the values of the states have some connection to their features. And in trying to make this function approximate that for this state, you also made it approximate it better to all the other states. You understand what I'm saying? The moment you do this, then you are talking about reinforcement learning with regression thrown in. Neat? Okay, and so that is one place where actually nobody questions factored representations. Many original reinforcement learning algorithms actually just sort of went with this sort of linear feature-based representations for the value function or the Q function. And then they try to set the W's, the weights, using learning methods. Now, the usual learning method in this case would be a gradient descent method. Okay. How many of you know gradient descent? Okay, so though I'll say a little, but so basically what you have in a gradient descent approach, actually let me, since we got all the way there, let me just talk about that, shift over these examples. Actually, let me just go through this quickly. I think I spent pretty much the class on this slide, and everything else is just examples. Okay, so learning generalization possibilities. Q-learning can now directly update the weights, for example, the factored representation. So, for example, the weights in a linear summation formula. The moment, how do you do it? You use a regression, and the regression typically tends to use like gradient descent, for example. And this sort of gives implicit generalization. Again, these points are not obvious, at least to me, when I first started thinking about it. So I'm sort of maybe if it's obvious to you, I'm sort of boring you to death. But if not, I hope you understand what's the advantage of higher level representations. Learnability, learning possibility just becomes very much front and center once you have, in some sense, in representing in representing the values of all states by a single formula, you already generalize their values. If in fact every state's value is completely different from every other state's value, and there is no way of predicting it at all, even at the 0th iteration, you could never have written an expression like this. You did some kind of a curve fitting. The state's values are all over the place, and you put one nice hyperplane and say, yeah, that's a pretty good hyperplane. That sort of comes close enough to everybody's values. And then if somebody's value, I have a better idea, then I try to tilt the hyperplane so that it becomes closer to this guy. In doing so, it becomes closer to hopefully everybody else. That's exactly what learning is. Okay? And then, of course, there are also other ways of learning that I don't go into so much. I won't be able to go into so much. But for example, when you have structure of the plan, you can then do a lot more in terms of, for example, in terms of reusing a previous computation. The moment you know the structure, you can reuse the previous computation. So one of the points I made to you guys is, if I know how to go from S1 to S2, etc., up to Sn, okay, and I did S1, and instead of going into S2, I went to S5, I don't have to give up. The plan still is there, because from S5, I still know what to do. Okay, that is just generalizing, an entity that was only, a plan that was only made for S1 to Sn to also work for S5 to Sn. That's generalization, however primitive it is. And you can do a lot more interesting generalizations if you start seeing that S1 and S5 are really made up of Boolean variables. And so you then wind up saying, well, it looks like any time a state has this Boolean variable true, this false, this true, the length of a plan for going from there to a goal state tends to be at least 15. That's a useful information. Okay, so that's also the kind of generalization you can get. The funny thing is that people would not talk about any of this, because if you just go directly into propositional representations, you don't ask, why am I doing propositional representations? Okay, but however, since we started from state space atomic representations, we owe it to ourselves to ask ourselves, why exactly is it good? And answering that question turns out to be quite fundamental, not just for MDPs and reinforcement learning. It's across the board. As I said, when we go from propositional to relational, some of the same issues come up. Okay, so let me try now to run you past some of the rest of the slides. So anyway, I think this stuff basically is saying that all actions will be S by S, and they will all be large. Now, whereas if you have state variable models, if there is locality, you can exploit it. An example of approaches that use the locality is trips actions. Okay, so basically now each action is talking only in terms of the state variables whose values it cares about and the state variables whose values it will change. And then implicitly the transition matrix is defined. Again, the way one way of thinking about it is that atomic representations ultimately will be the limit h tends to 0 f of x plus h minus f of x by h representation of differentiation. You see what I'm saying? If you ever question, why the heck do you say that this particular derivative is this? I can always take you back all the way to the limits. And this is how the derivative is defined. And that's the basis. Okay, so soundness and completeness and everything has to be done at the atomic level. That's why you didn't waste your time. You understood something in atomic level. So at least if you are using some ADD approach, let's say, to prove that it's sound and complete, you need to do it. The proof has to be at the atomic level. And then once you prove it, you can just blindly use your algorithm. Right? Okay, so all these actions I can write. If you force me, I can write state transition matrices. So then you will have the action representation, the state transition matrices. Okay, and then in planning, for example, there are representations that they developed, Lisp-like languages that they developed for writing these actions. I mean, I wrote them in some nice rectangles. Planning community has its own representation called PDDL, Planning Domain Description Language, which allows you to represent this. Okay, that's one language. Now, just as How many assembly languages are there in the world? Maybe a handful. How many higher level languages are there? Like a gazillion billion. And apparently there's never any good one, because everybody comes up and says, all the higher level languages suck. I am coming up with the right one. Okay? Nobody ever seems to say, all the assembly languages suck. I will come up with a new one. Why not? Okay? And similarly, people will come up with lots and lots of representations, higher level representations, because nobody is happy with any single one. Okay? There was a question. Yes?
What are those functions mean?
Which ones?
Like on table?
These are all propositions. On table X is a Boolean proposition. It can be true or false. Okay? So that's a representation that basically can write, you can take it down, and then the advantage, as I said, this strips representation is if there is locality to be exploited, you can exploit it this way. You see what I'm saying? If there isn't any locality, in fact, if it turns out that a particular action is quite complicated, it depends on, it has a very different outcome in every different state, and there is no obvious pattern at all, writing it in this representation will still make it really big. In fact, it will be just as big as before, plus some extra parentheses. And this is the same thing for higher level languages. Ask yourself the following question. If I give you an arbitrary piece of assembly language, can you always convert it into a small piece of C code? No. An arbitrary piece of assembly language might correspond to 3 pages of C code. But most of the time, you would like to write, most of the things that you write, a 3-page or 2-line C code might become 2 pages assembly thing, and that's what you keep focusing on. Oh, look how I avoided writing 2 pages assembly code. Okay, but if I give you a 1-page assembly code, I can force you to write 3-page C code, depending on how crazy that code thing is. If there is no obvious connection as to, there is no loop structure or no, locality anywhere, what do you do? Okay, so that's something to keep in mind, that higher level representations are basically aimed at using the structure if it is available. The tricky part is different representations try to capture different kinds of structure. Okay, much of this, for example, I know that some of you may have taken various data mining-ish, machine learning-ish courses. And there would be this issue of, okay, I can do decision trees, I can do naive-Bayes classifier, I can do support vector machines, I can do neural networks. What should I do? The same question. It depends on what structure you're trying to capture. Okay. Anyway, so that's that. And then factor representations, the strips ones, of course, were deterministic. So to do for MDPs, you need to talk about uncertainty. Okay, there is obvious way of directly, extending the strip representation called probabilistic strips operators, which essentially, so basically they kind of say under these conditions, this is the strips operation. Under these conditions, this is the strips action representation. So they will give different sets of preconditions and effects for each possible branch. The alternative is to realize essentially, and in fact this kind of goes much more nicely into the next topic we'll be looking at, Bayes networks. Okay, so what I would do in the second one is I would just write all the state variables, suppose they're Boolean, okay, all the state variables in the current time slice, t-1, and then all the same state variables in the next time slice, t. An action somehow connects their state variable values from previous level to this level. And this is a graphical model. It has arrows, right? Okay, and it turns out that it is actually a Bayes network, which is kind of interesting because this is a graduate course, so you should know Bayes networks, but I know that you don't, so I'll talk about it next week. But I'll right now assume that you know Bayes networks. Okay, and so Bayes networks, these are Bayes networks, and these are dynamic Bayes networks. They are Bayes networks which are connecting value of state variables in one time slice to the values of the same state variables in the next time slice. Now it turns out for any given representation, for any given particular world where you can represent what the world actions are in English, I can provide you this kind of 2TBN representation, or I can provide you PSO representation of actions. Which one is better? First of all, you can have religious arguments, okay, and secondly, the answer depends. Answer depends. In fact, it can be argued that when there is no obvious kind of structure that basically allows you to capture an action as just a union of 5 different strips operators, this won't work well, this works better. So let me show it to you in a minute. Okay, so the idea I'm saying is that once I define an action, then I'm trying to write it as, I define the action to you in English. Okay, you're trying to write it as either a PSO representation or a 2TBN representation. If there is like a small finite number of PSOs, the strips operators that completely capture these actions, this particular action representation, then you would go with PSO. If not, 2TBN will always work, because it's a much more generalized representation. And to put this in perspective, when probabilistic planning competition started, the first idea they used, they have to have this is a class, so I can say you can use this or you can use that or whatever you feel like. But if it's a competition, I need to give a specific standard so that everybody eats action representations in that standard, right? And so the first representation that people went for is PPDDL. Probabilistic PDDL. Since PDDL was strips operators, probabilistic PDDL was basically probabilistic strips operators. And then after a while, there was this other guy, a researcher, Scott Sanner. This also, by the way, is kind of interesting about you're coming close enough to the edge of any of the research that you kind of see the sociology of science. Okay, so one way you can make, suppose there is a religious argument going on as to one representation versus another representation, okay, and your side is losing. You can make it win by actually volunteering to hold a competition that everybody wants to join and say that you must use this particular language. You spend a lot of time, but you could win. Of course, you could also lose badly because nobody joins your competition, so you wasted a lot of time setting it up. That's possible too. Okay, but this is how science works actually. It's not necessarily the case that there is no obvious, I can prove theorems as to when this will work versus the other one will work. Is there, long back I saw somebody wearing this t-shirt. It said 25 years of research into programming languages and C++ is the result, ? Okay, so that's the result. Of all the research into programming languages, a lot of people are really unhappy that C++ is something like the standard. Why did it become the standard? It has nothing to do with whether it's the right or wrong language. It's a lot of sociology involved. Anyway, so the first time PPDDL was used, which is PSOs, I'll give you an example of it in a minute. And then the next one, when Scott Sanner, after like 3 times of running it, there was nobody to run it. Scott Sanner was asked, and Scott said, okay, I'll run it if you get rid of this very bad language called PPDDL and use my language called RDDDL. Okay, the RDDDL is 2TBN representation. Okay, now a lot of people complained, saying our planners work with the previous language. Then he said, okay, I'll let you enter the competition. I will laboriously give the RDDL description as well as a translator from RDDL to PDDL in those cases where the translation is possible. So you can feel as if you're still solving the problem. Okay, whereas other people can still work directly on RDDL. That's a native. So right now RDDL is being used in the community, for example. Okay, and it happened because Scott said, hey, 6-7 months of my life, who cares? I'll just spend it. And that's how he made it happen. Okay, now there are obviously interesting theoretical differences between the representations you can talk about, but that wasn't the reason as to why one gets taken versus other. Okay, so this is actually a good example of like a general MDP-ish domain where this is a coffee, I'll basically this one is from a Jair paper by Boutillier and Hanks and co. It's like a 92-page behemoth of a paper that basically talks about MDPs and POMDPs and value iteration. I'll send you a link to it. But you don't need the algorithms themselves because we already discussed them. Okay. But they also have this example there, a nice example, and they talk about the high-level representations for actions there too. Okay. So here is a a robot domain, and then these are the features. You have these features, and here are the actions. And the English description of the features is given here. English description of the action is given here. And then the question, of course, is how do you represent these actions, for example? And one of the nice things they show is you can represent the actions either this way, which is the PSO representation, probabilistic strips operator representation. Just like I said, notice that it says if a particular variable is true, then go this way, false, go that way, and if this variable has a value O, go this way, otherwise go this way. If you go this way, then the strips representation of your action you're supposed to use is this. If you go this way, the strips representation of the action you're supposed to use is this. Remember, these are all probabilistic, so they need to throw in essentially the probabilities. Okay, and in fact, one of the things that makes it strips operators is that it provides, when you come here, either you would get these as the outcomes with 0.19 probability, or these as the outcomes with 0.76 probability, or these as the outcomes 0.01, or these as the outcomes 0.04. All I need to know is given a state, given this action, can I compute the next state? Or the distribution of the next state? I can. That's all I need. So this is the PSO representation. This can be directly converted into PPDDL language. Okay, again, I'm not giving you the syntax of the language. As I said, I mostly want you to understand the kinds of representation that can be used and what are the various advantages, disadvantages. Okay. Whereas the alternative way of representing it is this. Okay, here essentially this is a time t and time t plus 1, the same set of variables. And there is a Bayes network which essentially connects those variables. By the way, in this particular Bayes network, you may have noticed that there are no arrows within the same slice, same time slice. What that means is that the individual features are probabilistically independent. That's not always the case. Maybe some features are probabilistically related to other features. Sometimes some features are deterministically related to other features. In blocks world, in the very simple blocks world, the feature clear A is related to the features somebody is on top of A. If nobody is on top of A, then A is clear. Do you see what I'm saying? Again, if I would say that certain features are independent, if I give you, let's say I have a feature set of, let's say 10,000 features. I'll say it's independent. If even after I give you 9,999 features values, you still are in no better position to guess the 10,000th features value as you were in the beginning. Do you understand what I'm saying? Whereas obviously clear and on are not independent that way. If I tell you nobody is on this you, then I also told you you're clear. See what I'm saying? Okay, so when the fact that there are no links here means currently they are all independent features. If you want to consider representations where the features have correlations, you can also have links there. And that would be a Bayes network that is basically, that's correlating both the inter-slice and intra-slice. Now, the one thing that you want to understand about Bayes networks, which I hope you all know already, is if you have a node, and it has k parents, That's what the topology of the Bayes network says. I need to provide a conditional distribution of the value this particular node could take, the probability, let's say, suppose it's a Boolean variable. I want, what's the probability that this will be true given these guys are true, 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 false, false, blah, blah, blah. That's the conditional probability distribution I have to provide. When I provide that to you, then I have provided you the Bayes network. Not surprisingly, you notice that this guy CR is dependent on the location, RHC, and CR. And so it requires a nice big conditional probability table like this. Now, again, when we start talking about Bayes networks, we will look at discrete, extensional representations of the distribution, the discrete distributions. But eventually, these representations become too unwieldy. They're too big because there's too many different variations that the parents can take. And in particular, if either the parents or the child is continuous, you can't write a table. There is no table that's big enough to write. Right? So eventually, you take these tables and you write parameterized distributions. And again, I want you to understand that when you parameterize a distribution, you are generalizing it. There is no real normal distribution ever. I mean, do you guys get marks in normal distribution? No. I mean, you'll get some marks which is sort of, there's somebody like this, somebody like this, somebody like this. Oh, that's nice for normal distribution. I threw in a car. Right? I just said that, I mean, really, if I don't want to lose any data, I should keep your entire distribution of marks. Who the heck has that kind of time? Plus, if I have normal distribution, then I get to summarize the entire distribution in terms of two numbers, mu and sigma, and I'm happy. It's the same kind of issues that you do when you talk about whether to go with one representation versus another representation. You see, in fact, I mentioned this in the context of particle filters. Okay, the reason Kalman is such a hard guy is because under the conditions of assumptions of normally distributed, conditional normal distribution as well as normal distribution as the uncertainty as well as the sensor model, you will always get a normal distribution outside. Otherwise, even if you start with a happy normal distribution, it will start becoming very peaked, and then you need a lot more parameters to keep a representation of it. Okay, but anyway, so that's a representation of actions here with PSOs, with two TBNs. And then finally, for the rewards, here I use the reward functions are being represented, and reward and values typically use the same representation, right? And they are represented in this case as ADDs. So now, if I were to represent, of course, I understand I can either have taken this or taken this, pick one. And then I have considered the reward functions this way. Okay, now the question is, how do you do value iteration on this? Well, the simple idea is to convert everything back into states. And then, do the value iteration, and then before I come, close the thing, and then I say, here is a close enough, ADD. Okay, but that is actually an easy thing to do algorithmically because you have an algorithm already for that. Okay, but it won't take into account any efficiencies that you could potentially get by having these representations. So to actually use the representations directly, you need to use the representation of the reward and the representation of the reward and the representation of the actions. The PSO actions are the 2TBN actions, to directly go from initial reward, which is the V0, to the V1, to V2, and so on. I'm not even going to tell you how you should do it, okay? But that's what you need to understand. If you come up with a representation and you really care about it, then you want to show what would be the Bellman update in that representation. And the great thing is, although Bellman update is supposed to work on individual states, once you generalize it, it's now going to work on whole sets of states together. See what I'm saying? And there are algorithms, for example, for doing this, and they look nothing at all like the simple two-line algorithms you have seen, but they're essentially doing. And once they write that algorithm, they prove that it is actually doing the Bellman update. If you were to compile it, this is what Bellman update would have done. And then once they prove it, you can stop worrying about it. You can directly do, direct, ADD level changes. And one of the reasons ADDs are particularly popular is because, as I mentioned earlier, ADDs look like BDDs, except they have numbers instead of true false values. And there is an entire community out there which talked about how to do all sorts of interesting operations directly on BDDs. Okay, such that the operation size would be polynomial. I mean, the operation complexity would be polynomial in the size of the BDD. That's not bad. And so people tend to use those to kind of come up with ADD modification operations. Okay, so there is actually an old planner called SPUDS, which basically uses ADDs, and then it takes the action representation and takes the reward function and comes up with a new ADD representation for V1, V2, etc. Okay, so this is the direct manipulations of ADDs in SPUD. And then notice that there are all sorts of interesting things, like you can multiply diagrams, you can add diagrams, etc., because you can add value functions, multiply value functions, etc. Okay, so they all become, the moment you get into this, what matters more is you understand ADDs and still remember Bellman update. Okay. Okay, so I think I will stop here. I will, however, when I come back next class, talk a little about reinforcement learning with lifted representations, because that actually is quite useful in terms of actually the question that we would be looking at in the case of reinforcement learning for the lifted representations is if I were to tell you for a bunch of states whose feature values are given, this is the correct value for these states. Can you then find me a linear function over those features that closely captures the value distribution? This is a learning problem. I've given you, people's names and people's features, and then I told their expected height, and you're trying to learn a function, a regression, find a function which will actually predict the heights for a new guy. Now the interesting thing is, that regression is typically done by just changing the coefficient values for each of the features. As you change the feature coefficient values, that's how you change the curve fitting. Regression is nothing but curve fitting. Okay, and once you understand that, the Q-learning and the TD learning steps can be essentially seen as not as changing the value of the current state by updating it using the value of the next state, using the alphas that you thought, except it's just directly changing the thetas, the weights. And since once you change the weights, the moment you change the weight to make your value approximation be closer to the current state, you also change it in other places, whether you like it or not. And if your representation is good, in very few steps, you would learn a lot about the value function. That would have taken a lot more time if you went state by state by state. Do you see what I'm saying? We will get back to this point next class and then go from there to Bayes networks.